Okay, so Chris, it's my pleasure to introduce Chris, who's a research assistant in the University of Cambridge, and he's going to tell us about promising ARM RISC-V concurrency.
Yeah, thank you. And this is joint work with Jean Pichon Farabo, Ji-Hoon Kang, Sang-Wan Lee, and Gil Hua. Right, so concurrency programming is very difficult to get right, and that's especially true with relaxed memory models. What's a relaxed memory model? The memory model of a programming language is the part of its semantics that defines the concurrency behavior, and in particular the concurrency behavior you get from the shared memory interaction between the concurrently executing threads. And then relaxed memory models are memory models that only give weaker guarantees about this concurrency behavior, and they're found in many programming languages like C, C++, Rust, and Java, and most hardware architectures, including x86, ARM, RISC-V, and POWER. Now, just to sort of illustrate the problem and this relaxed memory behavior, if you imagine you're a programmer and you're writing a piece of concurrent software, let's say for message passing between threads, then it might look like this in a simple case. This library has two functions, one for sending data from one thread to another and one for receiving. The send function takes as an argument this integer v and then writes that value to the shared location d, and then sets the flag f, the shared flag f, to let other threads know that this data is now available. And then the receive function is running in a loop, and it keeps reading the value of f, and when it sees the value of f set to 1, it breaks out of the loop and reads the value of d and returns that value. So a test case for this program might be one where we just run in parallel two threads, one that sends the value 42 and the other one that receives. Now, for this program to work correctly, we'd expect that if we started off in a state where d and f were initially 0, then we'd get the outcome that the receiver sees the value 42. But if we took this program and compiled it to ARM, for example, and ran it on your phone that probably has an ARM chip inside, then a possible outcome would also be that the receiver sees the value r equals 0. And the reason is the relaxed memory behavior that we didn't take correctly into account when writing this program. So this program, the way I've written it, is broken, and it has two bugs due to this relaxed memory behavior. The first one is on the sender side, where we've got these two writes to d and to f, and they're not related in any way, and they're two different locations. And so if we compile it, the underlying machine might try to optimize the performance and might come to the conclusion that it's better to execute the write of f early before the write of d. And now, because ARM has this relaxed memory semantics, the result of this optimization is allowed to become visible in the programmer observable behavior. And so, for example, the receiver might see the value of f being updated to 1 before the data has been written yet, and then lead to returning r equals 0. So that's the first bug. The second bug is on the receiving side, and it's a bit more subtle. So here, the way we've written the program, just control flow wise, we can only get to the point of reading this value of d if the flag has been seen as being set to 1. But again, the hardware in the background might try to optimize this program and might make the guess that eventually we're going to break out of this loop. And so the hardware has branch speculation, and the branch speculation might lead it to execute this read of d before the read of f to try improve the performance. And this could again lead to, because the relaxed memory behavior of ARM allows this, this could lead to the receiver reading 0 for the data and 1 for the flag. So that's the two bugs in this program. And it's we can fix this by adding certain ordering annotations on two of the accesses, and the details don't matter. This isn't even valid C code the way I've written it here. The point is only it's easy to get this wrong, and the behavior isn't, I mean, it's not obvious at all. So what's needed at this point for the programmer is a precise definition of this concurrency behavior, written in an understandable way, and so that ideally the programmer can avoid making mistakes like this from the start. But then ideally that also be tool support to try catch errors like this earlier on in the development. And here we're trying to make some steps towards that for the ARM and RISC-V processor architectures. So why target these architectures? One reason for us not to target programming language concurrency models is that at this point, there's still no generally accepted sensible concurrency definition at this language level, because they all suffer from a problem called the thin air problem, which is another topic. Targeting machine models therefore has the advantage that the concurrency semantics is generally better understood. Another advantage is that while necessarily the semantics and tools we're going to arrive at will be specific to these architectures, they will, on the other hand, work for any programming language that we are coming from if you're compiling the code, and you don't have to trust the compiler. And then another advantage is that we can more easily handle features like inline assembly that are difficult to do at the level of the programming language. And here we're doing this for ARM, which is a widely used processor architecture with a fairly subtle concurrency semantics, and RISC-V, a newer architecture that recently adopted a very similar model. Now for these two architectures, there are already two formal specifications of the concurrency behavior, partly from our past work on this. And they're in two different formats. One is the official reference axiomatic models for ARM and RISC-V. And axiomatic here means that they're specified in terms of axioms over completed executions. So they specify some sort of validity condition for a completed execution to be architecturally okay. An advantage of these axiomatic models is that they're usually nicely abstract and fairly concise, but the downside is that they do not work incrementally. So they're specified as these global axioms of completed executions. And then on the other side, there's the operational models, and operational means abstract machine models. So you have states and transitions, and that's our flat model for ARM and RISC-V, which has been proved equivalent to that axiomatic model. And an advantage of these operational models is that they, as abstract machine models, they work incrementally. So they have a good step-by-step intuition behind them. And another advantage is that they've been designed to be in a closer relation to the hardware. They're abstracting from the microarchitectural mechanisms found in the processors, and so are in good correspondence to this hardware. But as a result, are also fairly complex. So this flat model has, for example, explicit branch speculation. And the way it expresses the concurrency behavior is that you have multiple transitions, many transitions for each instruction. So that's complicated to understand. And so here we try to come up with a model that tries to combine the advantages of both to get an operational model that has the sort of abstractness or small size of the axiomatic models. And this model is called the promising ARM or promising RISC-V model. And it's based on the ideas of the promising semantics for C11 concurrency, but here applied to these architectural models. We've got a Coq proof of equivalence of this model with respect to the axiomatic model for both ARM and RISC-V, although this excludes, this is purely for the concurrency behavior. It excludes the sort of the detailed semantics of the assembly instructions, sort of the sequential aspects of these assembly instructions. And based on this model, we've built an executable tool that is fast enough for model checking smaller examples of concurrent data structures, smaller but realistic examples. And I should say up front, compared to this flat model, there's two main things that aren't supported yet. One is mixed size memory accesses. So here we're assuming at this point that memory accesses all have the same size, which we're planning to lift that limitation. And at the moment, but this is just engineering, it's missing the definitions for atomic memory operations, but these are essentially the same concurrency-wise as load store exclusive instructions, which the model does handle.
Can I ask you a question, Chris?
Yeah.
In model checking, smaller than what? You just mean
small. Smaller than bigger. Smaller than bigger examples.
They're small enough to analyze them, otherwise it's too.
Sorry?
So you're saying you can model check examples as long as they're small enough to not overwhelm your tool? Yeah,
so I'll get back to the model checking part of it later, and I wrote down the examples that we've tried it on. So those are things like lock implementations or concurrent data structures. And well, we're trying to remember the examples. There's some spin lock, I think, from.
Onto that. Did you see? If you come to that later, I don't.
Yeah. I can.
But is that related to this cock? I mean, it's a separate bullet point. But is that unrelated to this cock work you mentioned?
Yeah. So we've got, in some sense. So we wrote up two specifications. We have the specification language called lem, which can export theorem prover definitions and executable OCaml code. The executable tool is based on this. And this is the model that's integrated with semantics for the full, well, the user mode instruction behavior, like the assembly instructions. The cock model is a separate definition. And this is, I think, mostly because the lem, well, the output from the lem tool for cock isn't great. We didn't target that. So those definitions were written specifically for proof. So there is a gap here between these, but we've written them to be in sync. Yeah.
Okay. And what's generally the role of proof assistants like cock in this area? I mean, in some regards, these systems are seen as, as the most rigorous way that you can treat certain problems, right? And certainly, if you can formalize correctness or of some scheme in cock, then you're feeling good about yourself, right? You've probably done it at the greatest level of rigor anyone's going to ask you to do. But I mean, I would have imagined that it's typically in this area of real world hardware unrealistic to hope for verifications at that level. So, but am I wrong about that?
Oh, so just to clarify the question, I guess, is this related to the model checking part as well? Because
that's what I'm exploring.
Of course, so this part is a proof. Just to make sure we're understanding each other. This is the cock equivalence proof proves that this model is equivalent to a different presentation of the same semantics. It's not something that happens at the level of the programs that we're checking. So this is a tool for checking programs. This is something about the semantics. So as for the role in general, the problem is with these definitions, they tend to get really big and complicated, these concurrency model semantics. And the other equivalence proof I refer to from past work, this has been done as a hand proof. And here we just tried our best and wanted to have the formalization if possible. And it was a lot of work that mostly my co-authors from Seoul National University, they mostly did this cock formalization. And it's just, it's quite easy to get it wrong with these concurrency semantics, as with other big complicated semantics definitions, it's easy to get it wrong. And so the cock formalization gave us extra confidence that this correspondence holds. We also proved some lemmas that are useful for validating the optimizations we do later, but then of course, taking into account that there's this gap between the Coq formalization and this executable tool.
Maybe I can chip in a gloss. So, Jamie, so you're right that the effort for these Coq proofs is sometimes just unavailable. But then on the other hand, we're very conscious of the fact that we and other people have got proofs like this wrong in the past without machine checking them, because they're quite finicky. So it's a difficult situation.
So you're saying it would be desirable to be able to work at that level of rigor, but it's difficult.
Yeah, it's very highly desirable, but it's also sometimes, but not always, prohibitive amount of effort.
Understood.
Yeah. So at this point,
I have a question, actually, since we're asking questions. Does anybody know the answer to this? I mean, I don't know whether, Christopher, you do or not, but so software developers write programs which very often got bugs in. We all know that. Is it known even approximately what proportion of those bugs are due to the bizarre real-world semantics of out-of-order instructions and branch speculation and so on, and what proportion are due to, as it were, more routine errors?
Yeah, I don't have any numbers. Maybe Peter does. I can only say one thing that makes it harder to even catch these bugs is the sort of non-deterministic nature. So you might run the program, and it requires a particular combination of compiler and hardware maybe for this bug to show up, because you might that particular combination, and then you have to run it a couple of thousand times or million times until you see that behavior once. So statistically, it doesn't happen very often, and that makes it easier for some of those bugs to go undetected. So,
or you have a bug that appears in production and not in development because of differences in the.
Yeah. So this is part of what makes it useful to work on these semantics, is that, well, on semantics and tools, is that testing just doesn't work very well for this, because you'd have to have available a variety of hardware to even start doing the testing you'd need to do to reliably find these mistakes. And even then, it might be that the compiler output slightly changes and it exposes the bug that you had all along, but you didn't catch it during the testing. Don't know if Peter has available any idea of numbers of bugs. I think I don't.
I don't think I've got much to add to your answer. So I think the majority of bugs will probably not be to do with this kind of thing. But what you said is very true, that this kind of bug is very terrible, and hence people are quite motivated in the industry to use more rigorous techniques in ways that other parts of the industry have not caught on to. Even things, so one instructive data point maybe is that when quite some time ago we found a hardware bug in IBM Power processors, that was something that even with aggressive testing we could only see in, I don't know, 1 in 10 to the 10 instances or something, and that would be very hard to find with normal testing, but was still common enough to warrant quite a lot of attention from the hardware people.
So there's a little conversation happening in chat. Can we have the conversation in the real virtual universe? Because the one person who can't see the chat is Chris, because he's sharing the screen and he can't see it.
One other thing that is maybe relevant is that while these bugs, you're likely to encounter these bugs roughly never in normal programming. The place where you might encounter them is in operating systems and concurrent routines in JITs and stuff, where they're really, really bad places to have bugs.
Yeah.
I think I can input one last thing here, which is that even though these are incredibly rare for like an individual to see such a failure, when you're Linux and you're running hundreds of millions of machines at once, somebody is going to run into the bug. So just because it's rare doesn't mean it doesn't happen very often.
Well, that's a great discussion.
Thanks, everybody, for answering my question. Perhaps
You'll crack on, Chris.
Chris should continue. Yeah.
Okay, so there's these limitations. Let's see. Yeah, so in the following, I'll give a sort of brief overview and walk through some examples to try to give you an idea of how that model works. So just to give a rough idea of this concurrency behavior, so on ARM and RISC-V, generally, any two memory accesses that you have on the same thread will be unordered by default. But then the architecture gives you some facilities to restore this ordering if you need it. And this is memory barriers and certain memory accesses called release-acquire accesses. Those create ordering between memory accesses on the same thread. And then certain data flow and certain control flow dependencies between memory accesses also create memory model ordering. So as a result, you get a fairly subtle concurrency semantics. The model tries to explain all these behaviors, the allowed and the forbidden behaviors, using three main concepts or three main ideas. First idea is that when you have out of order reads happening, then the model explains this by having a sort of fancier memory state. The model records in its memory state the history of all the writes it has ever seen, and then sometimes allows memory reads to read from older writes in this message history, corresponding to these memory reads happening early, effectively. Then to regain some of the ordering that the architecture guarantees, for example, for a memory read, allowing it to always read arbitrarily old reads, allowing the read to read arbitrarily old writes in this message history would not capture the correct semantics. So this has to be constrained. And so in the semantics, there's something called a view. The thread state will contain a couple of views that effectively constrain the timing of the memory accesses with respect to this message history. And then the third idea is that for explaining out of order writes, there's a concept called promises. The idea is that an early write, a write done out of order, is a promise, and the thread can make a promise of a memory write at any time if it will be able to later fulfill this promise, regardless of other threads' behaviors. Now, these are probably fairly unclear at this point, but I'll just walk through some examples to try to give you a better idea of this. The example is this one, which is the same example as before, just now compiled to some sort of fake assembly language, where thread 1 is executing the code of the send function. It's sending the value 42 by writing it to the location D and then setting the flag. And thread 2 is running the code for the receive function. So it's reading the value F, and here it's saving that into this register R1. All the things named R1, R2, and so on will be registers. It checks whether R1 is equal to 1, and if so, it goes and reads the data, and otherwise does something else, which I omit here. And so the interesting execution, or the sort of buggy execution from the point of view of our program, is the one where thread 2 reads the flag being set to 1, but then sees 0 as the value for the data. Now, one of the explanations for this buggy behavior in the original program was that the two reads on the receiving side could be executed out of order and speculatively, this load of D before the load of F. And the model explains that using this message history. So below the program, if we assume we just go into the initial state, below these boxes show part of the memory model state, sorry, the operational model state, hides a couple of things, but at the start we have some sort of standard register state for the threads, mapping registers to values, and a memory state that is a list of the writes we've seen so far. And if we just start executing and execute thread 1, then the store of d equals 42 will just add a write to this message history. And so does the write of f equals 1. It adds this corresponding write message to this message history. And if we now execute thread 2 and this load of f, any load is always allowed to read from the most recent write in the message history. So we can read this write f equals 1. And that updates the register state. And the condition evaluates to true. And we get to executing the load of d. Now the load of d could also read from the recent write d equals 42 in the message history. But reads are also allowed to read from older writes. In this particular case, this initial write that sets everything to 0. And if that's what we do, then that sets the register state for R2. Right, these are the two writes we could read from.
So do you mean that's non-deterministic?
The semantics is non-deterministic, and for understanding all the behaviors, you have to consider all the options.
Okay.
Yes. Mm-hmm. So at this point, the way to get to the interesting behavior is the one where we read from this initial write, which sets the register state of R2 to 0 and gives us this interesting sort of bad outcome. I was saying earlier, allowing reads to read from arbitrarily old writes it would not capture the semantics of the architecture correctly. One of the things that that constrains the order of the execution is data flow dependencies. And so here I've tweaked the program to include something called an address dependency between the two loads on the receiver side. So the load of f, the result is saved in register R1. And here the expression that computes the address of the load of d now involves R1. It does plus R1 and minus R1. And so we know that the address will not actually depend on the value of R1, but the syntactic dependency is enough to guarantee the ordering. Meaning the load of d now has to happen effectively after the load of f. And in the semantics, that's captured by this notion of a view. And the idea is, in the memory state, we have these write messages, and each write message receives a timestamp when it enters memory. And the timestamp is just the index of this write in the list that is the memory state. And a view is now the timestamp of a write that has been seen in some sense by the thread. These views appear in a couple of places of the semantics, and one of the places is the register state, which maps registers to values, but additionally view annotations. So the idea is that there's some sort of taint tracking going on, where we always record the most recent write in memory that the register value depended on. And this constrains the instructions that involve this register. So if we jump to this state of the execution where we've done thread 1 and done the two writes, propagated the two writes into memory, then they will have gotten timestamps like this. The initial state has timestamp 0. Sorry, the initial write has timestamp 0. D equals 42 at timestamp 1, f equals 1 at timestamp 2. And if we now start executing thread 2, then when we read from f using this load, this will, so I should say, if we read again from this write that sets the flag to 1, which has timestamp 2, in addition to setting the register state to 1, it adds this view annotation 2, just recording that this is the write that this register value depends on. Then the condition evaluates to true, and if we get to executing this load of d now, because this expression involves the the view, sorry, it involves the register 1, which has this view 2. This read is constrained to effectively happen after timestamp 2. And if we check in the memory state, at timestamp 2, this write of d equals 42 at timestamp 1 has overwritten the initial write for d. And so that means we can't read from that write anymore with this load because it has to happen after that timestamp 2 effectively.
I have another question.
Yeah.
So, you know, being shown this material just makes you become more and more paranoid about the meaning of anything.
Mm-hmm.
Presumably in these architectures, does expression evaluation, can that happen in out of order ways? I mean, is it possible in thread 2 for R2 to get loaded with -1 because somehow you subtracted R1 from the initial value 0 and then it loaded it too quickly?
So I should say I'm cheating here a bit because this, as I said, it's this fake assembly language. Of course, the real assembly language has instructions and all the results are tracked. So there's no expressions. But
yeah, I see.
It's tracked via registers. But then there's certain guarantees that also these relaxed memory models don't touch in some sense. And one of them is the fundamental guarantee that basically if you look at one thread in isolation, then it behaves as expected. You do not, for example, if you write to X and you read from your own write, I mean, you're not allowed to overlook that write. And this is, I mean, the same is true for registers. You will read the most recent write to that register, although there are also weird exceptions there apparently for special purpose registers, but normal kind of code you'd write wouldn't be affected by this. Yes. Mm-hmm. Right. So that explains or gives an idea of this this ordering for memory reads. Right. In the full semantics, there's a bunch more of these views to handle other kind of ordering between memory accesses, as resulting from barriers, release, acquire, instructions, coherence, and other things. These are all handled using these views. And right, the third idea in that list I started with was the thing that explains the out-of-order execution of writes. And that the idea is using this concept of promises, which gives the semantics its name. So if you remember from the example at the start, there were 2 bugs in that program. Now we've changed the receiving side to have this ordering between the reads, and that fixes the reader side. But on the writer side, we have the 2 writes that are unordered, and the hardware might execute this load of the store of F early. This notion of out-of-order writes is explained using promises here. And the way this is specified in the semantics is that a thread can promise any write to do any write at any point in time if it will later be able to fulfill this promise in a way that is independent of the behavior of other threads. I'll just show you how this works out for this execution. If we start from the initial state, then one of the things thread 1 can immediately do is do this write early. And the way it does that in this semantics is it makes the promise to do a write of F equals 1. And doing this promise means that this write is added to the message history with its timestamp, and to all other threads other than thread 1, this write is just like any other. But for thread 1, it comes with the additional obligation to fulfill this promise and fulfill it at the right timestamp. So if we just continue executing and do this store of d equals 42 normally now, that adds another write message to the message history. And we're now at the point where we can execute the store of F equals 1. And now because we've got an outstanding promise for this instruction, for this store here, instead of making a new write, this store will now fulfill this outstanding promise. And fulfilling this promise just means we remove it from this set of promises in the thread state. And now we can, and I'll skip over that, because now the two writes are in reversed order, the views will work out in the right way on thread 2 to again allow this relaxed execution where the load of F sees 1 and then the load of D sees 0. Now, I think maybe in the interest of time, I'll skip over this. The idea is that writes and promises are subject to the same kind of view ordering as reads. And this is again explained using views. Now in this execution, the idea was that, so I should say, in this example, we stick a release annotation on this thread. And whatever that means, it guarantees that the two stores happen in program order. So this execution where this write of f equals 1 is done early will not work out. And trying to make it work, the semantics would make a promise, but then get stuck with an unfulfilled promise. So the semantics has an extra condition because these sort of stuck states are undesirable to have in an operational semantics if you can avoid it. The semantics has an extra condition called certification that avoids these stuck states for unfulfilled promises. And the idea is that whenever a thread T makes a step from some thread state S to some thread state S prime, we apply an extra check that checks whether S prime is a good kind of a thread state to reach, namely one where we can ensure all the promises will be fulfilled. And the exact check for this is that from S prime, we require that T can execute purely sequentially, that is without making any new promises, from S prime to some final thread state alone, so without the interaction with other threads, to some state where it fulfills all its promises. And I think I'll again skip over the details for this. This example is just replaying the same example with the release where the certification then prevents this bad behavior, where the execution gets stuck. So I'll just skip over that. But the main idea is that this certification step that avoids the stuck states is a purely thread local check.
Christopher, I have a question. So in the promising semantics, you have the timestamp on F. I understood that it's a promise to assign to F in the future, but you've given it the timestamp of at 1.
Yeah, so let's see, if I go back to this example. So if you make a promise, and it behaves like a normal write, it goes into memory and receives a timestamp. So if we're in this example and promise to do the write, if we promise the write of f equals 1 from this state, then it enters memory as the next write. Yeah. And because it's the next write, it receives timestamp 1. So you have no choice of where to promise it or when to promise it.
Okay, the promise doesn't include a specification of exactly when it's going to happen.
So it does, and it becomes an obligation. So if you that's the thing that might be counterintuitive here. And it's the thing that prevents this execution. So in thread 1, if you promise the write of f equals 1 as the first thing, then it enters memory at timestamp 1. But then in order for this to be okay, you have to make sure you will be able to fulfill it as happening at timestamp 1. And in this particular example, it will not work out because you will execute the write of D, which enters at timestamp 2, just because it's the next free timestamp. But because this instruction is a release write, its view will include the view of the preceding store. That's not always true.
Yeah.
But because it's a release write, it has to now happen at a view greater or equal to the store before it. The store before it was at timestamp 2. but we promise to make it at timestamp 1. And so this is where the semantics would then get stuck, because you've got an unfulfilled promise to do this right at timestamp 1, and you've got timestamp 2. So this is the thing that in this semantics then keeps these two stores in order. And I should say, in conjunction with, well, this thread local check, that means you wouldn't even go down the execution path where you reach the stuck state, because that's the thing this certification is supposed to prevent.
Okay, so although the write in some sense happens later, it's assigned the timestamp when the promise was made.
Yeah. Yeah.
Thanks.
Okay, so that was the part about certification. So I should just say, to sort of summarize, this was supposed to give you an idea of the sort of three main mechanisms the model uses. There's the full concurrency semantics has a lot of detail, and there's some subtle distinctions and ordering requirements to take care of. These are all dealt fairly uniformly using additional views that the thread state keeps track of. And then there's some extra machinery for load and store exclusive instructions, which I have no time to explain here. So I just thought I'd briefly talk about this executable tool that we've built on top of it. So as I said, it's the model that we use to get this executable tool, it's specified in this specification language called lem, which you can use to generate executable OCaml from it. And then there's also a bunch of existing work on the Sail specification language that is a specification language for the sequential aspects of the instruction behavior. So there's been a lot of work on Sail as a language, Sail, the ISA models that we integrate, and ARMm, which is a collection of executable operational models that promising is one of. So we use ARMm's infrastructure for this executable tool, and we use it to produce this tool. And one of the ways of using it is as follows: you give it an ARMv8 or RISC-V binary as an input, or also a litmus test, where litmus tests are the particular sort of format targeted by these kinds of tools. And you can tell the model to run that program exhaustively for loop-bounded instances of smaller concurrent programs, and get out a list of all the possible states you can reach when running this program, each with a witnessing trace. And then the idea is you can check whether these final states match your expectation of the program behavior and see if there's any unexpected buggy executions. And if so, you take the witnessing trace, put it back into the model, and replay it interactively to try figure out where it is that things go wrong while stepping through the operational semantics. So the part we've concentrated on in this work was mostly the first part, the exhaustive execution, where if that's what you want to do, enumerate all the possible states, then exploring all the possible traces and combinations of transitions is too expensive because there's far too many interleavings to explore. So we need to optimize this naive approach to make it feasible to run these programs. And there we've used two main optimizations that sort of exploit sort of interesting properties this promising model has. And the first one, the main one, is the one where it turns out that if you have a trace in this promising model, a trace TR, then for any such trace, there exists an equivalent trace, TR prime, which basically reorders the transitions of the first trace, but in an equivalent way, such that the trace you get is one that does all the promises first and then all the non-promise transitions. So first, of course, if you restrict the model to only exploring traces of this shape, then that cuts down the non-determinism a lot, and it saves us performance. But on top of that, another optimization applies, and that's based on the observation that if you do all the promise steps first, basically at the point where you've done all the promises, the final memory state is fixed. So all the writes you can do in the semantics can also be promised in principle. If you explore all the promise transitions first, you arrive at the final memory state, but you don't know what the final thread states are yet. So the non-promise transitions then essentially explore what final thread states are possible under this memory state. And we can then do that in parallel because at this point, there's no interaction between the threads anymore. So that's the two main optimizations. With those, we run a couple of examples. And the idea is we write it as C, C++, or Rust code, compile it with a standard compiler. At the point where we were doing that, we didn't support the binary format yet. So we mapped it to this litmus format with a script and then ran the tool to enumerate the final states. And we did that with a bunch of examples, like I think that's a Linux spinlock variant and some sort of textbook concurrent algorithm things. And the biggest examples we tried were the chase left DQ, I think, and the Michael and Scott Q. And I forget exactly the detail. I seem to remember it was between 100 and 200 lines of C code, and it produced a similar amount of assembly code as an output. And then we ran that in some variations with, well, up to 2 or 3 loop unrollings per thread with a couple of threads. That's sort of the size of program we were targeting. And well, we collected some performance results, and it compares favorably against this flat operational model tool and the axiomatic tool as well, which I'm not showing here. Those tools were never designed with for model checking in mind, and so the comparison isn't so interesting. The main result is that the model is fast enough to use it for some interesting examples. And that gets me to the conclusion. So we've built this model, promising ARM, promising RISC-V. We think it's a simpler operational concurrency model that explains the ARM and RISC-V concurrency behavior. On top of it, we've built this executable tool that you can use for exhaustively checking smaller examples and interactively debugging them, for which we have some sort of useful performance results. This was published in PLDI 19. But in the meantime, I should say, Michalis and Victor Vafeyades have, in the meantime, produced a tool called HMC, which is based on stateless model checking. And this tool is faster than ours. So this has happened in the meantime. That tool is based on LLVM, but it does work with the architectural concurrency semantics. And I've got some links in case you're interested in checking these models or tools. The source code is online. Well, and I just wanted to hint that there's two things we want to do with it in the future. One is that in the meantime, or in parallel, we've been working on extending our concurrency models with more sort of systems aspects of the behavior, including the relaxed semantics of instruction fetches and self-modifying code. And there's ongoing work on page table accesses. And when I say we, this is, first of all, Ben Simner. So one of the things we'd like to do is eventually extend promising in the same way to handle their semantics. And then another thing we're planning to do is work on correctness proof of concurrent software. And with Jean Puchon-Farabo, we're working on a program logic built on top of this promising model. And yeah, that's it. Thank you.
Okay, thanks very much, Chris, for a very nice talk. I'm going to ask everybody to unmute, and then we can applaud to thank Chris for his talk. Okay, thanks. Now mute yourselves again. All right. So we've had some questions already, but I wonder if we've certainly got time to have some more discussion.
Mm-hmm.
I wonder if anybody can ask Chris a question. Just go ahead and unmute yourself.
I have a probably very silly question. when you reorder all the promises to the front and you get an equivalent trace, like
Yep.
if you have a branch in the program that
Mhm.
changes which writes will be committed, like, it
Mhm.
seems unobvious that you'll be able to move those promises to the front. Is that just a different set? Is there only one promise set of promises at the start, or do you have one per like possible branch
Yeah,
structure?
so that's a good question, and it's I guess I haven't really explained enough about how this promise mechanism works, because the thing is, in order to check which promises are possible, so there's this idea of certification, and the idea is before you're allowed to make a promise, you have to sort of, the thread that wants to make the promise has to prove that there is a fulfilling trace for this thread alone under the current memory state. So if you assume you're in some state and there's some branching going on, then you have to show with that just with the memory state you've got available at the moment, you could choose the read values in a particular way that would allow you to go down a path in this control flow to make that promise. Because otherwise the certification fails, right? You need a store somewhere in that control flow that justifies the promise you're about to make. And so when I say here, when I say here you can do all the promise transitions up front, this is hiding something a bit. So this might look like it's a bit cheaper than it really is, because in order to detect whether these are valid promise steps, you do have to do some of the work you would do otherwise in non-promise transitions. So you have to somehow explore some possible thread behaviors before you know that those promises are possible. So the precondition of these transitions hides some of the work that is going on, if that makes sense.
Yeah, that makes sense. Thank you.
Mm-hmm.
Any other questions? I wanted to ask about the thin air problem. I know it's maybe not directly related, maybe to your results. Maybe you could talk about that briefly.
Yeah. So the thin air problem in general, I mean, this came up at the very start, is a problem that exists in defining a sensible concurrency semantics at the programming language level. So it turns out that the architecture has these relaxed memory models. In addition to this, when you have your C program, let's say, and you compile it to some architecture, the compiler also does certain optimizations. The combination of the two give you a very, if you want to accommodate for both, and for a language like C, you want to allow these optimizations, and you want to allow mapping constructs of the language to these relaxed accesses in the architecture, then you get the combination of the relaxed behavior from both in some sense. So that gives you a very weak semantics. And it turns out defining a semantics as weak as that isn't sort of broken in some very particular way, namely that it generates these thin air values, is very tricky. And what a thin air value is there is that, well, you might have your program generate read or write values that don't appear to be justified really by what you've written in your program. And I should point to, I mean, if you're interested in reading about this, one of the things to read is Jean Pichon's PhD thesis on this topic. And then there's been a couple of other papers after that.
Thank you. Very interesting.
Actually, I should say, one thing that's funny is, I mean, I'm pointing at the thin air problem as a justification for us not to target the programming language semantics. But at the same time, the promising semantics, whose ideas we're building on, is one of the proposals for a solution to this problem. So we're sort of importing those results that are really aimed at solving this thin air problem and applying them in to these architectural models here.
Thanks.
Mhm.
So any more questions for Chris? Okay, in that case, I guess we can thank Chris again for a great talk. Thanks again. I'll unmute
Thank you.
again. Let's just thank Chris again for his.
Thank you.